Hello everyone, today we are presenting our project from Mechatronics titled Simulation and Implementation of a Robust Fuzzy-PID Controller for a 6DUF Quad Rotor. This project was done under the supervision of Dr. Kalantari and presented by Kosar Amin Jafari and Mohammad Reza Sharifi. Here is outline of our presentation. We start with an introduction, then review the literature, explain our control design, and finally show MATLAB Simulink implementation and result. Quad rotor are become important in real-world applications such as logistics, inspection, and rescue. However, they are inherently unstable, nonlinear, and under-actuated system, which make control very challenging. In real environments, unpredictable factors like wind gusts and payload change make the problem even harder, and a standard controller often fail. Our solution is to design robust Fuzzy-PID controller that ensure stability and accuracy under these uncertain conditions. Here, we compare some classical control strategies. The PID controller is the most common. It's simple, it's easy to tune, and doesn't require a mathematical model. However, it performs poorly for highly nonlinear system, has a high probability of error, and needs manual tuning. The LQR controller is based on const function optimization. It's powerful for linear system and can handle multiple input and output, but it requires a linear model, and its practice it may still suffer from a steady state error. The backstepping method is a systematic design for nonlinear system, ensuring stability through Lyapunov theory. However, it often suffers from what is called complexity explosion, meaning too many parameters and a very complicated implementation. More advanced strategies have also been developed. A sliding mode control, or SMC, is very robust against disturbance and uncertainties, but it suffers from this chattering problem, which can damage actuators, and it requires knowledge of disturbance bounds. Model Predictive Control, or MPC, offer robust performance and predictive capability, but it comes at a high computational cost and a strong dependency on accurate model. Adaptive control allows online parameter tuning, which helps to deal with time-varying uncertainties. However, the stability analysis is complex and is often very sensitive to noise. Finally, reinforcement learning can learn optimal policies without a precise model of the system. It's robust against unknown dynamic. However, it faces a big gap between simulation and real-world application and requires a lot of training data with safety concerns. So, while each method has its strength, they also comes with significant weakness. That is why in our project we propose a hybrid Fuzzy-PID controller, which combines the simplicity of a PID with the adaptability of fuzzy logic. The standard PID controller is simple and popular, but it has fixed gain, meaning the values of Chi-P, Chi-I, and Chi-D are tuned only for one specific condition. In real life, quad rotors face nonlinear dynamic, such as aggressive maneuver and environmental change like wind gas or payload. Under these conditions, the PID loses performance. In short, PID is a static controller, while the quadrotor is a highly dynamic system. Therefore, we need a smarter and more adaptive solution. Instead of relying on a precise mathematical model, it uses a linguistic rule such as if error is large, then apply a large correction. This makes it robust against uncertainties and changes in system parameters. Since fuzzy logic is inherently nonlinear, it's well suited to handle the complex dynamic of quadrotors. We combine the advantage of both methods into a hybrid Fuzzy-PID controller. Here, the PID partakes as a muscle providing the core control action, while fuzzy logic acts as the adaptive brain intelligently tuning the PID gains in real time. The fuzzy system continuously monitors the flight error and its rate of change, and dynamically adjusts Kp, Ki, and Kd. As a result, we obtain an auto-tuning and adaptive controller that maintains a stable performance even when flight conditions change. Now, this block diagram shows how the position controller generates commands for roll, pitch, yaw, and attitude, which are then sent to the motors. The plant represents the quadrotor that updates its state based on these commands. Here we see the quadrotor tracking a 3D trajectory in simulation. The results show that the system maintains stability while following the desired path. These plots compares the desired and actual response for position and angles. The results confirm good tracking performance with small errors. Now, this diagram shows the attitude control loop where roll, pitch, yaw, and attitude commands are converted into motor signals. The quadrotor dynamic then updates to reflect the new state. And this graph illustrates the tracking of roll, pitch, yaw, and attitude. The actual output follows the desired commands with acceptable accuracy and stability. Fuzzy-PID for attitude control. These block diagrams represent the Fuzzy-PID structure for attitude control. The fuzzy logic adapts the PID gains in real time to improve stability under varying conditions. Here we see the fuzzy inference system calculating Kp, Ki, and Kd based on the error and its changes. This makes the controller adaptive and more effective than a classical PID. These surfaces show the fuzzy rules used to adjust the control gains. They illustrate how the system responds differently depending on the error and its rate of change. And the tracking result for roll, pitch, yaw, and attitude show that the Fuzzy-PID controller provides a smooth and accurate response. Compared to the standard PID, it reduces overshoots and ensures faster convergence. For the hardware implementation, we used an MPU 9250 IMU sensor together with a discovery board. The IMU provides real-time measurements of acceleration, angular velocity, and orientation, which were essential for feedback in the controller. The discovery board was responsible for processing these signals and running the Fuzzy-PID algorithm to control the quadcopter. Thank you for attention.